All right. So some of the things that we covered last week, I'm not going to cover all the content, but I'll try to hit some of the high points. So first off, the midterm. So the midterm is this upcoming week. It will be written. It will be part multiple choice. So we'll be covering all the content to this point. We'll have about 25 multiple choice questions and about 6 short answer essay questions. Short answer are about 4 to 6, about 4 sentences. I'd say 6 is the absolute maximum. So the multiple choice will be over the concepts. We're not covering any kind of SQL or looking for you to memorize the Amazon interface or anything like that. It's really to test the concepts about tell me about the difference between some specific products, like when would you use Athena versus Elastic MapReduce, or how does Athena differ from a database, things like that. So to really try to test your knowledge of the content as opposed to specific minutia about different parts of it. All right, and so I'll make this video to cover some of the high points that we discussed in class, and then there'll be another video for the lab and homework. So the very first bit of it is this 3.0 Hadoop architecture. So really the focus areas are how distributed processing happens. So we've already talked about that we have a cluster. Cluster is a group of our computers. We have a master node that organizes all the workers, and daemons are programs that run on a node. So a program is like anything that you'd run on your own computer, like Microsoft Word or any applications that you'd run yourself. Hadoop, which is the open source distributed programming framework we're talking about, has a number of different daemons or programs that run on the servers that make it work, basically. So there are 3 main components that come together to make Hadoop work. There's the processing component. So this is the actual compute power, the CPUs. The storage, so the disk or the storage space, and then the resource manager that manages the processing and storage resources. And so we have a cluster. The cluster has processing power or compute. It also has storage, and the resource manager negotiates how jobs get allocation for the processor, and how files get split up on the storage, basically. And so backwards, there we go. So HDFS, so we're not going to talk about HDFS a ton because we use S3 instead of HDFS. But HDFS is what comes with Hadoop by default. It's the Hadoop distributed file system. It is written in Java, and it's basically a file system on top of your file system. So like this graphic shows, you have your storage, your actual physical hard disks. Then you have the operating system file system. So if you're in Windows, it's the actual Windows file system where you store files. And then HDFS actually runs on top of that. It runs on top of your operating system file system. And so that basically just means it's like a program that runs on your computer in a way. And that makes it a little bit less efficient than your native operating file system. But it allows us to do some different things with it, basically, like distribute the files across the cluster like we do. But it will never be quite as efficient or low level as what's built right into your native file system. The core of this is that Hadoop performs best with a modest number of large files. That means that we try to keep it to the thousands or hundreds of thousands of files in a folder, and this is true also for S3. And so basically we want fewer big files instead of more small files, and the files are write once. So like we talked about, if we modify a file, it actually gets deleted, and a new one is written with the modifications rather than changing it, which is different than how your machine works. This is just describing how a file gets split up into blocks. Blocks are 128 meg chunks. So if we have a 4 gigabyte file, we split it into a bunch of small chunks. We separate those chunks across the cluster, and you'll notice we have at least 3 copies of every piece of data, every chunk of data. That way, if we lose any machines, we always have 2 other copies if we lose one machine. And so this is how your file system works. Your computer splits large files into blocks. It just splits them into very small blocks, like 4 kilobyte blocks, as opposed to what we have here, which are like the 4 gigabyte blocks that you're seeing referenced here. We're not going to talk about this. We're not covering this. We're not covering that. These are on the excluded slides. We use Hue in the homework. Yarn is a resource manager, so something has to take the jobs, the queries, or other kinds of processing jobs that we give to a cluster that we give to Hadoop, and break it into tasks, and then assign those tasks to workers in our cluster, right? So that is what Yarn, yet another resource negotiator, does. Is it takes a job, a query, some kind of analysis that you want to run. It breaks it into tasks. It split those tasks up across the cluster. And so we have one resource manager, so it basically allocates out the cluster's resources, the compute, the memory, and it can have pluggable schedulers, which basically means we can get pretty sophisticated with how we want to manage the resources. So companies like Facebook have written pretty sophisticated algorithms for how work gets assigned across the cluster and who gets what resources when, basically. We don't have to worry too much about all the intricacies of that. And then the node manager actually runs on all those workers, and it communicates back to the resource manager. It basically says, hey, I'm up, I'm ready, I'm waiting for work, and here's how many resources I have available for you. Containers actually run your tasks. So a job, it gets broken into tasks. A task runs in a container. So we can have multiple containers on a worker, and these are basically just what run our jobs. So a task runs in a container, and one worker or machine in a cluster can have one or more containers. Bigger machines with more resources have more containers. Smaller machines with fewer resources have fewer containers. And then an application master actually orchestrates a job. And so we'll see here that if I store data, it gets chunked up into those blocks I talked about, which by default are just 128 megabyte pieces of data. If I submit a job to the resource manager, I say, hey, resource manager, run this query, run this application, give me this analysis. The resource manager says, hey, worker, you're not doing anything. Start up an application master in a container. That application master says, hey, name node, which we're not worrying about because we're not talking about HDFS, but it basically says, hey, where's the data you stored? And it says, okay, I know where the data is. I need these 2 resources. I need 2 containers. The resource manager says, hey, you 2, you're not doing anything, start up 2 containers. And then it says application master, you can use those. And so then it takes your job, it breaks it into 2 tasks on the containers in these 2 workers, and they run. And once those tasks are done, the application master continues to monitor them. It says, hey, how are you guys doing on your tasks? How are you guys doing on your tasks? Once they're finished, it says, okay, I'm done, and it gives you the results. And so all these run in containers. If you have more applications or jobs, you have more masters, application masters. And so you could basically have hundreds of different jobs or applications running across a cluster in parallel. And so we're not going to worry about any of this. We will use the Hue job browser to view how our jobs are going. But we won't worry about any of this stuff right here. And that's it. All right. Now EMR. So EMR is Elastic MapReduce. It's going. So Elastic MapReduce. So we've been talking about Hadoop for the last 9 minutes now. So Hadoop is an open source distributed compute processing framework. So it's what takes the jobs, it distributes them into tasks, it runs the tasks, and it monitors the tasks. Elastic MapReduce is Amazon's Hadoop as a service offering. It allows us to deploy Hadoop clusters on demand, paying by the node by the hour. So basically, they take care of the installation, they take care of the configuration, and they give us a Hadoop cluster that's ready for us to use, ready for us to write queries on, ready for us to store data on, do whatever we need to do. EMR clusters are platform as a service, so AWS manages the patching and software installation. So they're platform as a service as opposed to infrastructure or software as a service. So EMR clusters are ideal for transient workloads. So basically that means if I have something, I say, hey, overnight I want to compute my sales figures for the past 24 hours every night. And as soon as I'm done, I want to store it in a database and power dashboard. That's a transient workload. I need a cluster to run that computation, to run that processing. But after that, I don't need that cluster anymore, right? I need something to read the data, run my query or my job, and save the data, and then I can turn it off. I'm done with it. That's a transient workload. EMR is perfect for that. And so we can schedule EMR clusters to start up, to run a job, and then to turn off. And of course, we stop paying for them. EMR deploys clusters into NSGs. Those are network security groups, and we'll see an example of that in the lab. But NSGs are basically just where we configure networking rules, and those are just the rules that govern which computers can talk to which other computers and basically what they can say to each other. So it's functionally a firewall like what you would have at home if you have a router or something like that. And again, we'll see an example of that. EMR clusters can be configured with any of the major Hadoop projects. So Hadoop is more like an umbrella of different pieces of software or packages of software. So we talked a little bit about HBase on the first night. It's just a key value data store. Not going to test you over it. You don't need to know it. Scoop is just the solution that copies data from databases into Hadoop. And usually that's used if I want to take a database and copy it and then do something like large-scale analytics on it. That's a very common use case for Scoop. And then Presto is actually kind of like Hive. It's a query engine, and it's if you remember the Hive lecture, Presto is basically the exact same thing. It lets us query files that are stored in HDFS or S3, and Presto is what Athena is based on. Spark is the distributed processing framework. We've talked about it a little bit. We'll talk about it more later on. Pig is I've talked about, but we won't cover in any depth. But it's basically like the poor version of Hive. It takes a syntax called Pig Latin. It converts it into MapReduce code, and if you remember, MapReduce code is just the code. It's basically a programming framework that takes a program and breaks it up into tasks and runs it across the cluster, right? So it's just the thing that takes our jobs, splits it up, and runs it in parallel. Zookeeper we won't talk about it in great detail either, but it's a project that helps you run distributed applications. And then Hive we've talked about quite a bit, and Hue we will use in the lab. And so these solutions, these projects, they can be mixed and matched during cluster deployment time, and we'll see that in our EMR lab. So custom apps can be added using the Bootstrap actions. So we have a whole lot of choices out of the box with EMR because it's a PaaS service. But if we need to add something that's not already included, like Cumulo or Flink, which are solutions we will not be talking about, don't worry about it too much. But basically the crux here is you can install whatever it is that you need for your use case, even if it doesn't come out of the box. EMR clusters can be deployed programmatically. That means I can write custom code, I can write custom applications that go out to AWS and they say, hey, deploy me an Elastic MapReduce cluster, make it this size, make it this version, run this job on it, and then when that job is done, tear it down. And so I can do things like the overnight job I talked about, where if I want to process my sales by store every night, I can do that, and I can use EMR for that, and I can make that an automatic job that runs every night. The EMR clusters can auto-scale, so that means they can dynamically expand or contract based on usage. So if I have a really heavy job running, I can tell EMR to automatically scale up to 16 worker machines if I want. And whenever it's not being used as much, I can have it scaled down to 2, and that just helps me with cost management. So unlike most on-premise Hadoop clusters, the storage and processing for EMR are decoupled. So we talked a whole lot about how files get broken up into chunks, into blocks. Those blocks get stored on the workers, right? Well, since we're using S3, which we used last week to store all our files, that doesn't actually happen. S3 holds all the data, and all that data gets copied to our cluster, which is good because S3 is very cheap. EMR gets very expensive, and that allows us to turn the EMR on, use it when we need it, turn it off, stop using it when we don't need it. But it also means that we do have to copy all of the data to our machines anytime we need them. So that is the only downside. So different instance types are suitable for different workloads. So we'll see that there are a whole bunch of different types of EMR machines, and that some of them come with a lot more compute power, some of them come with a lot more memory, some of them come with really fast disks, and that totally depends on what kind of job you have. If you're doing a very complex, very challenging algorithm, then maybe you'd need machines with more compute and less memory. And if you have a whole lot of data, but you're not doing very complex transformations, maybe you would need the opposite. And so there are a whole bunch of different machine types with different characteristics in Amazon, and you can pick the right one to optimize for what you're using, for what you're trying to do. Basically, is the thing here. And then finally, spot instances are suitable for workers, since their state can be transient. So in Amazon, you can pay retail price if you want for a machine, and that's what we'll do in our lab. But as a company, if you want to try to save some money, you could actually bid on a machine. You could basically say, hey, Amazon, I don't want to pay you retail price. You want 30 cents for that, I'll pay you 20 cents for that. And if they have free capacity and nobody bids more, they'll give you that machine for 20 cents instead of 30 some cents, right? But the downside with spot instances is as soon as anybody comes along and either bids a higher price or pays retail, your machine will get taken from you without warning. And so that's probably not great if you're trying to run an application or run something really important. But if you are running a worker and maybe you want to do your master machine that we saw in the previous slide as a pay by the hour instance, and your workers by bidding on spot instances, you could do that, right? And if you get some extra capacity, you save some money. And if not, your job just takes a little longer. And so the deal is spot instances are much cheaper than regular instances, but they can be revoked. Amazon will turn them off without warning. That's fine for your workers, since their tasks will be reallocated to other machines, right? If Amazon takes back 1 out of your 8 workers, or even 4 out of your 8, those tasks will just go and fail and be reassigned to the existing 4. So your job will just take longer. But if not, you'll save a bunch of money, right? So spot instances are a great way to save money if you're a company by bidding on Amazon capacity. I already talked about that slide. That's duplicate. And then finally, EMR versus Athena. So Athena is preferable for querying and producing a result set when the query is relatively simple, right? So Athena is great if you have a pretty straightforward query. It only supports jobs that run for 30 minutes. So if you have a ton of data or you have a really complex query, I can tell you from experience, it can take longer than 30 minutes. And once it hits 30 minutes, Athena will just kill your query. It just cancels it. So really complex queries on really large data sets, they're not suitable for Athena. It just won't succeed, right? Athena only supports a subset of SQL commands, so we can't do inserts or updates, so we can't change anything about the data. EMR's Hive supports a subset also, but it has many more commands, including insert and update. So using EMR, we can do inserts and updates. And then EMR supports the development of complex applications using Spark or MapReduce. So basically, Athena is great for relatively simple and queries with small to medium data sets where you don't need to change the data. It's great for that. It's better than EMR because it's easier to set up and configure. EMR is better for more complex queries or when you need to use a huge amount of data or modify the data, right? And so that's kind of the difference between those two at a high level. All right, data formats. I'll talk about this just a little bit. So basically, we saw in the very first night that we were using text files, right? Text files are the kind of thing that you can just download and open with Notepad or something similar. And so we saw this kind of query where it was stored as text file. That is the default. So text files are the most basic file type in Hadoop. They can be read and written to virtually any programming language. So almost anything can read and write text files. We saw a tab delimited file when we used Athena, and text files are human readable. So you can open Notepad and it makes sense. But it's also very inefficient. It represents basically everything as strings, even numbers as strings. So it takes a lot of space on your hard drive and in memory. It's very difficult to store images and videos as text files, and we have a conversion penalty. So basically, text files are very good for interoperability. Almost everything can read and write them. You can just open them with Notepad and look at them. But the performance is terrible. They are very inefficient from a space and network copy perspective and a memory perspective. Sequence files are a little bit different. We're not really going to worry about these too much, but they're basically just key value pairs. So a key is like maybe the term in a dictionary, and the value would be the definition of in that dictionary, right? Or a key would be your customer ID number, and then they would look up all the information about you. So key value pairs are very flexible because the key can be anything and the value can be anything, but they're pretty inefficient. So in this case, the performance is better, but the interoperability is poor. Avro is more relevant. So Avro is efficient because it's an optimized format. It's its own format. You can't open it using Notepad, right? It's like a zip file. If you try to open a zip file with Notepad, it won't work. It'll look like a bunch of gibberish. So it's custom format. It's custom encoding, which is what that means, and it's widely supported through Hadoop. So Avro is its own project. It's outside of Hadoop. And it's used by most of the things in Hadoop. Spark reads it, Hive reads it, MapReduce reads it, and a bunch of the other projects that we haven't talked about and won't talk about. And so it's a data format that can be read into and written from a number of different languages and solutions. It's good for long-term storage of data, so you can read and write from many programming languages. It embeds the schema in the file. The schema is what we did in that whenever we did that DDL and created a table, right? So we said, what's the column name? What's the kind of data in this column? Is it an integer, a floating point number, a date? That's the schema. It's what defines what the data is, right? What are the columns and what kind of data are in the columns? That's the schema. For Avro, the schema, that DDL like we did for the table, is written right there into the file. So if you have the file, you know information about it just by having that file, which isn't the case for something like CSV, right? A CSV doesn't tell me what the column should be called. Maybe that's the first record, maybe it's not, and then I definitely don't know what data type it is without inspecting that, right? So Avro is very handy for that, and then it can accommodate changes in the schema over time. So it has very good interoperability in the Hadoop and the big data ecosystem, and it has very good performance. So it's a very good general purpose file format. And so a little bit of context here for the next format is most databases store a row of data together. So in this case, we'd store that this was Alice, she lived in Palo Alto, and was an accountant together. This is how database is stored, is this row of data is stored together. For analytics, that's not that efficient. Usually what we want to do is query entire columns of data. And so usually what I want to say is like, what's the average salary in Palo Alto, right? Well, in that case, I need to read this entire city column and this entire income column, and I don't care about any of the other columns, right? And so a columnar format stores all of the data in a column together, and columnar formats are very good for analytics and data science type workloads where you want to do dashboards, you want to do queries and things like that on large segments of the data. Also because it's much more efficient to store the data this way, right? And so the data in the city column is much more similar to other data fields in the city column than in the income column, for example. And so because we're storing a bunch of numbers about income together, right, a bunch of integer numbers together, I can optimize this much better. I can compress this data much better than I can, since this row of data, right, ID is very different from name, which is very different from phone number in this record. But all the phone numbers are pretty similar, right? They're all numbers with dashes in them, right? And so I can do a lot of compression on that and optimizations. And so what we'll be using in the lab is a file format called Parquet. So it's a columnar format developed by Cloudera and Twitter, and it's supported by a whole bunch of projects. It's at least as widely supported now as Avro, and it embeds the schema in the file just like Avro does. So it uses optimizations that Google developed in a white paper they published on Dremel that allow us to reduce storage space and increase performance. And so it's very good, and it optimizes compression ideally when we're adding a bunch of records at a time, because it identifies routine patterns that it can encode more optimally. So it works with a lot of different solutions, and it has great performance. And so Parquet has actually become something of the default for analytics and data science workloads and big data. So Avro, we're not talking that much about serialization, deserialization. Not talking about data types. Not talking about that. And so what Avro does is allows us to change the schema over time. So if we want to add a column, if we want to remove a column, if we want to change the values of a column, change it from integers to floating point numbers maybe, Avro is pretty good at that because we can tell, since this file has the schema embedded, we can tell it, hey, I added this column and here's what you do with old data, right? So I can say, hey, maybe I didn't have an email address in some of the old files, right? Maybe those files didn't capture people's email addresses. Maybe that's new data. I say, okay, look, I added a new column. And for any files that don't have this column, treat all the data as null, right? Treat all the data as empty, or set a default value of no email address or as none or something like that. And so Avro, the bottom line is Avro allows us to add columns, to remove columns, and to change the data types in columns as our data changes over time, and to handle that more elegantly than some other file formats would, because that'd be a problem with some other solutions. All right, we're not worrying about any of this stuff. We're not worrying about any of that stuff. So data compression. So what we'll see in the lab is not only are we using Parquet, but we're also compressing the data we store in Parquet. So each file format may also support compression. Parquet does. Compression is basically me spending compute time, spending CPU time in order to save the amount of disk storage that I incur, the amount of storage I actually have to pay for, because my file will be smaller, right? But there's a trade-off there, so I can use a more aggressive compression algorithm that will take longer. It will take more compute time, which I have to pay for, but it will save me on disk space, which I also have to pay for. So there's a trade-off there that's ideal, right? How much time am I willing to wait? How much compute time am I willing to pay for? Versus how much storage time do I want to save, right? How much storage space do I want to save? And in some cases, compression can actually be a win-win-win, because many Hadoop jobs are I/O bound, which means input-output, which is basically how fast I can read and write from my storage or my hard drives. And so if I compress data the right amount, even though it takes me longer to compute that, it takes me longer to process that compression algorithm, I actually save on how much time it takes me to read and write that file when I save it. And so I can have a net savings of time, right? And so compression can also save on the performance of network transfers. So what we'll see is there's a continuum here on this next slide between the time required, or how much processing time it takes for me to compress the file. So Snappy is very fast, bzip2 is very slow, and the space saved. So the longer it takes me to compress a file, usually the more space I'll save, right? So bzip2 takes a long time to compress, but it also saves me a lot of space. Snappy doesn't take me very long, but it doesn't save me as much space. We will use Snappy. Snappy is a good default. What you'll find is bzip2 is not really like whatever, 1, 2, 3, 4, 5 times more efficient. In reality, we get a whole lot with Snappy. We save a lot of space. And then all of these are incremental, right? And so bzip2 is not usually very good it's not usually worth it. You'll see gzips for some files that you download from the internet, like from Kaggle. And so Snappy and gzip are the ones that I see the most frequently. But you have a choice, and that choice is basically a trade-off between how long it takes you to compress it and how much space you'll save once it's compressed. And so you can use Parquet and Snappy compression to optimize the data, save a ton of space, and reduce your file size. All right, we're not going to talk about that. So the bottom line is we can use file formats. Text file, almost anything can read and write, but it's not very efficient. Parquet is a really good columnar format. And we can not only optimize the file format, but we can compress the data. And so that was a super fast overview of the stuff that we